Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with another calculus tutorial. Today we're going to be discussing finding the area under a function or under a curve, and we'll be doing that by introducing a new concept called the definite integral. If you remember in class the past week, we were experimenting with finding the area under curves by blocking out the area under the curve with geometrical shapes that we could calculate their area. And we explored techniques for making those estimates more accurate. We arrived at a procedure where we sliced the area into rectangles and added up the area of the rectangles, and we found that we could make the estimate more accurate by making the rectangles in a narrower and narrower width. And we discussed that mathematician Riemann had investigated what happens as that width of the rectangles approach zero and created a concept called Riemann sums. Well, today, instead of the tedious process of adding up all those rectangles, we'll be looking at how to use calculus to get our answer. Our first definition here introduces a new concept or term called definite integrals. And it says here that f is a non-negative function and continuous on a closed interval a to b. And if we have that situation, we can find the area that is bounded by that function, the x-axis, and the vertical lines x equals a and x equals b by using this notation here, which is referred to as the definite integral of f of x. So again, you can see f of x is non-negative, meaning it's above the x-axis. So that's one bound of our region. Our x-axis is a lower bound of the region, and on the left and the right we have these two vertical lines. So we can see we have this closed-in region. I marked here with an R and shaded in pink. When we learn how to evaluate this definite integral, the number that we will be getting will be that area. Now in this definition, f must be above the x-axis, so that certainly limits our ability for some problems. And later in the tutorial series, we'll be discussing how we can extend this definition to find areas when f of x is not completely above the x-axis. Now, to calculate these definite integrals that we just introduced, two mathematicians discovered or invented the fundamental theorem of calculus. They discovered this kind of independently at approximately the same time. On the left here we have Sir Isaac Newton from England, and on the right Gottfried Leibniz from Germany, who both introduced and found this theorem. And what this theorem states is that we can evaluate this definite integral by first finding the indefinite integral, the antiderivative of f of x, and then using this notation we're going to evaluate that function using our two limits, meaning we're going to plug in the upper limit b into our antiderivative and calculate that value and subtract from it the similar calculation when we plug in a for x. So we're going to evaluate that. And this will work as long as we are able to find the antiderivative of our function. And remember, the relationship between antiderivatives and the original function is the derivative of the antiderivative gives us our original function. Now this notation here using the integral symbol was invented by Leibniz here in the year 1675. So let's apply this to some examples. Well, first, I forgot it here. I want to just clarify or restate. When we use this notation like this, this is an indefinite integral. So these are indefinite integrals. And there's no limits here. And an indefinite integral is a family of functions. Remember, we use that integration constant c to represent those family of functions. In this case, when we have these limits here, which will be numbers in our problems, these are now called definite integrals. And the result of a definite integral is not a function, it's a number. And as we just said in those previous definitions, that number represents the area under the curve. So let's look at an example here. First, we will just evaluate a definite integral to practice using the notation, and then we will apply that to area problems. So in this example, we have a expression raised to the nth power, so we have to use our substitution here. So u is going to be 4x plus 1, and u prime is 4. So remember, to use our integral rule we're trying to use here, we need u to the nth times u prime. So I need in my problem, I need here my u prime. So I have the dx here, but I need a 4. And to put the 4 here, remember we put the 1/4 out here. So to evaluate this, we're going to first find our antiderivative. So it's going to be 1/4 times u, which is 4x plus 1. We add 1 to the exponent and divide by the new exponent, plus c, and if we simplify, and that's got to be evaluated from 0 to 1. So if we simplify here, multiplying our fractions, we've got 4x plus 1 cubed over 12. Again, we're going to evaluate that from 0 to 1. Now, the fundamental theorem of calculus says that we can now plug in the 1 into this. So now I've got 4 times 1 plus 1, so we have 5 cubed over 12. Whoops, I forgot my c here. Plus c. So that's my f of b. And now we have to subtract plugging in a, the lower limit. So I'm going to get here 1/12, or 1 cubed over 12 plus c. And if we calculate that, we now have 125 over 12. And this number here, so minus 1/12. And then from the first part here, I've got c and then minus c. So notice these cancel each other out. And we end up here with 124 over 12, which can be reduced to 31/3. And that would be the value of this original definite integral here. Now notice the c's canceled out. So when we're evaluating definite integrals, we'll just drop the c. We won't write those because they're always going to cancel out when we do the subtraction here. So we can kind of forget that. So now you need to remember, if we're doing an indefinite integral, remember there'll be points off if you forget the c. But when we do the definite integrals, they're going to cancel out, so we can save a little bit of time by not writing those out. Now let's look at an area problem here. So I've got a function here, y equals x squared plus 1, a simple parabola, quadratic function. And we're wanting to find the area bounded by that function, the x-axis, and this interval. So remember, these intervals provide our vertical lines on the left and the right. And we're bounded on the bottom by the x-axis and our function here. So this is the region we're looking. And our fundamental theorem of algebra says that that area, now let me back up a second. What I needed to verify here was that our function is non-negative. So in this case, by sketching the graph of the function, I can see that f of x is above the x-axis. So we can apply our theorem. So this is the setup of the problem using a definite integral. And now we can find our antiderivative. So this would be x cubed over 3 using our power rule, and plus x using our constant rule. And we need to evaluate this using those endpoints. And again, I dropped the c based on what we just discussed. So now we can calculate. Now we're going to be doing a subtraction, so it's important that we put parentheses here so that we don't have any errors when we are distributing our negative signs. So now here I have 3 cubed, which is 27 over 3 plus 3, and then subtract, substituting in the lower limit. So here I've got 9 plus 3 is 12, minus here 4/3, and that's going to be 32/3, and that would be whatever the dimensions are, square units here. Now that's the area of this region here. Now let's look at if we, so as you can see, this can be done fairly straightforward. These functions were easy to integrate. As the functions get more difficult, the calculations can become more tedious. But what I want to show you next is if you have a graphing calculator, we can use the graphing calculator to evaluate these definite integrals. So our procedure when we use the graphing calculator will be to enter our bounding function into y1, and we'll graph that. The key thing to make the next step work out is that our left and right limits must be in the viewing window. If these are between -10 and 10, we can just use the standard zoom 6 to get the standard window. But if these numbers are outside of that interval, you need to adjust the window appropriately. And then we get into the calculation menu by pressing the second button and select item 7, and it's going to prompt you to enter the lower limit, which means the left side boundary, and then the upper limit, which means the right side boundary, and then hit enter. So let's go back and look at the two problems that we had and show the calculator for those. So let's go back here, bring up a graphing calculator, turn it on here. Let's go into y1, clear this out. So our original function here was 4x plus 1 quantity squared, and our interval is 0 to 1, so we can just use our standard window, zoom 6. I could zoom in here. Let me just zoom in here. It's not required to get our answer, but let's just, so that we can see what the calculator is doing, let's narrow our x range here. Let's go from, say, -1 to 2 on the x, just to expand this graph out a little bit. And now again, the third step was we press the second button and get the calc menu. And item 7 here you can see is an integral, and it's a definite integral. The graphing calculator will not do the symbolic integration. Now it's asking us here to enter the lower limit, which in our problem here is 0. Press enter. Now we put our upper limit, which is 1. Enter. And we can see here we got this decimal number. If we want to convert that to fraction, in case your problem is requesting that the answers be exact values, we can press the math button and convert that to a fraction. And we get 31/3 here, which is our answer that we got doing it using pen and paper. Now let's look at our area problem. So we would put our bounding function here, which was x squared plus 1. Clear this out. X squared plus 1. And again, we can press zoom 6. And now it's easy to verify that our function is above the x-axis. Now we can integrate using the second calc 7 menu selection, and our lower limit here is 1 and our upper limit is 3. And you can see the calculator is shading in and showing you visually the area that we're finding. And then again, we got a decimal number here, and to match it up with the answer we got doing it mathematically here, we can convert that to a fraction. And here we've got 32/3 again, which was the same answer that we had. So let's look at one more example, a more complicated one here. This will show you that it's going to be easier to do this using the graphing calculator. Now, we have recently learned how to graph this function. This is an e to the u, and we could create the u prime using this, but let's just use our graphing calculator since we have that. So now we need to enter our function. So we have second e to the x, and our exponent is 3 divided by x. And then divide that whole thing by x squared. And let's graph that, zoom 6. Oops, I didn't hit the graph button here. Let me go back on that. So zoom 6. Again, if we wanted to see this more clearly, we could zoom in. I'm not going to do that because our interval 1 to 3 is right there. So we can do second calc 7 and enter lower limit of 1, upper limit is 3. And we get here. Now this one won't convert to a fraction because e is a irrational number here. So our area for this problem, if we write down our answer, let's say we wanted to round it to say 2 decimal places, is 5.79 square units. So that kind of wrap up our first part of this. I don't want this to get too long. There will be a part 2 coming up where we will discuss some more complicated scenarios. We'll be discussing problems where, as we discussed, where f of x is below the x-axis, or maybe one where it's both above and below the x-axis, so we may have something that looks like that. And also we might have something where we have no explicit limits given, meaning we want to find the bounded in areas, so that would be, say, this area here. And so we'll be using finding x-intercepts, etc. So we'll talk about how to handle these scenarios in part 2. So good luck with finding your areas, and talk to you in part 2.
Are you ready? Are you ready? Oh, are